Hey Raiders, welcome back to my Loom Videos YouTube channel. Maybe you're seeing it there. I'm going to do this diagram, the greenhouse effect in the atmosphere and the carbon cycle, just as a way to help you review perhaps anything that you missed in class, or maybe you were not in class because of illness or travel or something else. So this will just be a quick video to help review how the greenhouse effect operates in the atmosphere. Keep in mind that there are good aspects to the greenhouse effect. We need the planet to be sort of held in a particular temperature range. Otherwise, life really wouldn't be possible for us. Even with all of our technology and engineering, one of the great things about our planet, one of the aspects of fine tuning is sort of within about, a 250 or 300 degree range. Even if you're at one of the poles where it's really cold, or in a equatorial sort of desert like the Sahara where things are really hot, it's still kind of in a limited range, maybe 120, 130 degrees, either above zero, above freezing, or below. And so we kind of have those types of that narrow window of things that we don't have, for instance, on planets like Mercury, where there are huge temperature ranges between the hot side of the planet and the cold side of the planet, depending upon which side is facing the sun. So the greenhouse effect in the atmosphere, of course, requires that we draw the sun. And from the sun, of course, we have ultraviolet radiation. We always just abbreviate this as UV. And of course, in the case of ultraviolet radiation, it comes through our atmosphere, makes it down toward the surface. I will put a couple of plants here, as is my custom, to indicate that we're at the surface. Maybe I'll add a sixth grader here. It's a big plant, either a big plant or a small sixth grader. And what we know about this ultraviolet radiation is that it will make it through the atmosphere. And as it comes down to Earth, something rather interesting happens here. Where the ultraviolet comes into contact with any particular surface, any object, we have something happen that is partial absorption of energy. And when some of the energy is absorbed, when the UV hits any sort of object or surface, we have a lengthening, leading to a lengthening of wavelength. So I want to make sure that you can see the whole diagram here. We have this partial absorption of energy, which leads to a lengthening of wavelength, so that what bounces off of the surface is no longer ultraviolet, but is in fact infrared. And we would expect that infrared radiation then to just kind of go back out into space. It does its job, sort of keeps the surface within that range that we talked about, in a livable range. But we have a problem. The infrared doesn't just kind of go back out into space, but it gets trapped here. And how does it get trapped? Well, it's our custom to draw maybe a power plant that is burning fossil fuels. So first, a lot of our power plants are in fact using fossil fuels. And what are they doing? They're burning those fuels. Now, burning is just the way that we talk about it, but scientifically we refer to that as combustion. And combustion is an oxidation reaction. So things are being exposed to oxygen, and that is leading to their oxidation. Now, from here we move on and we say, well, if burning is combustion, which is an oxidation reaction, what are the fossil fuels? Well, of course, one is coal. That is a solid. We have oil or petroleum. Of course, that is a liquid. And we have natural gas, which is, of course, a gas. We typically add the fact that natural gas, in its simplest form, is methane. Methane is CH4. It's carbon and hydrogen. All of these things are hydrocarbons. And when we burn hydrocarbons, mixing them with oxygen here in this oxidation reaction and combustion, we have things that are put out that are products of this reaction. As fossil fuels, these things that are made up of carbon and hydrogen, are burned, we produce things like carbon monoxide, carbon dioxide, certain nitrogen oxides, because remember, air is 78% nitrogen, and so we're going to be mixing nitrogen with oxygen. And of course, we're also mixing hydrogen with oxygen, so we also produce some H2O. Now, H2O is not a problem to have in the atmosphere. We know there's always a certain amount of humidity in the atmosphere. If the air is warmer, we tend to have a little bit more humidity in that air. Cooler air, colder air can't hold very much water vapor. But this is put out of a lot of power plants or other plants that are burning fossil fuels, but that would just be add to the humidity or perhaps lead to cloud formation up higher in the sky. We'll talk more about that at another time. Together, these types of things, and these aren't the only ones, but these things are called greenhouse gases. And just as glass in a greenhouse or thin plastic film in a greenhouse can trap infrared inside the greenhouse, the same way that your car in a parking lot, let's say the Costco or the Walmart parking lot, or some other parking lot, you leave your car in the parking lot in the summer, it's not running, but ultraviolet is coming through the glass. It's actually being converted to infrared as some of the energy is absorbed, maybe hitting the dashboard or hitting the seats or hitting whatever. But that infrared radiation is trapped inside the car, which leads it to become extremely hot. In the same way that that happens in a car or in a greenhouse, in the atmosphere, these greenhouse gases will trap this infrared so that when it comes up here, instead of just going off into space, it bounces back. It bounces back. And so here in the atmosphere, in the troposphere where we live, we end up getting atmospheric warming. And if that happens too much, that can lead to certain problems, right? If the atmosphere of Earth is getting warmer and warmer and warmer, that can lead to melting of the polar ice caps. It can lead to melting of glaciers. And that affects a lot of people. Whether it affects you directly or not, it affects a lot of people, especially those who are living in coastal areas. Think of island nations that are close to sea level. If those ice caps, if those glaciers melt, then sea level rises, and those people are possibly out of their home or out of their business because of rising sea level. But this is kind of how the greenhouse effect, in a negative sense, can operate in the atmosphere, where greenhouse gases trap infrared radiation, and that can lead to atmospheric warming. Now, one of the things that we talked about in class is that there are some alternatives to using fossil fuels. And so we'll draw this up here and draw, or just write here, suggested alternatives. As you'll recall in class, we talked about some of these. So we could use something like solar, or wind, or hydroelectric. But we also have things like geothermal and nuclear. Now, all of these other types of generating electricity, These are all valid things, but they can't all be used just in every place. There's some places that have more wind than other places. There's some places where even solar can be utilized more efficiently than other places. Places closer to the equator, or in some of the more temperate areas of our planet, warm or temperate areas of our planet, can use solar better than people could, let's say, near the North Pole or the South Pole, just because of the angle of the sun. There are also places that just have more sunny weather versus cloudy weather. And so you don't see a lot of people using a ton of solar panels, for instance, in places that tend to be really foggy, just because the intensity of the sun's light is not as great in those places. But these are all alternatives to burning fossil fuels: solar, wind, hydroelectric, geothermal, and nuclear. Again, geothermal isn't just everywhere. You have to have the proper geological conditions to have that kind of heat that you can utilize from within the earth. And wind, you have places that are windy, places that are not windy. You don't see the big white wind turbines just everywhere. You see them in places where they're more persistent, predictable, consistent winds. Yes. So these are alternatives to burning fossil fuels. But let's face it, fossil fuels are a good source of energy. We have ways of extracting these things from the earth, and we found them to be useful in since the Industrial Revolution for powering a lot of the things that we do in the modern world. But one of the things that you may not gather from, if you're listening to the news on the radio or on the television or something, you hear about the evils of using fossil fuel, but that's not the only part of this picture. That's why our heading up here, greenhouse effect in the atmosphere and the carbon cycle, we realize that there are things that are going on that are not just burning of fossil fuels, but there are other things that are putting carbon into the atmosphere, other than the burning of fuels, and taking things out of the atmosphere. And we refer to these as carbon sources. And over here we'll write carbon sinks, or what could be called reservoirs. Places that take up a lot of carbon, take carbon out of the atmosphere. So what are some of our carbon sources, and then what are our carbon sinks? Well, as we've already indicated, one carbon source is simply the burning of fuels. I could say the burning of fossil fuels, but actually any burning of fuels could lead to putting carbon into the atmosphere. The reason I'm shying away from just talking about fossil fuels is even if you're burning wood in a fireplace, if you're burning a fuel, you're going to be generating carbon dioxide. You're going to be producing a certain number of these greenhouse gases. So the burning of fuels is clearly a carbon source. Another natural carbon source would be volcanic eruptions. Some volcanic systems actually are putting out significant amounts of carbon dioxide. Also, some other things are put out. Sulfur dioxide can be something that's put out of a lot, and that can lead to acid rain. So acid rain is often associated with burning of dirty coal that has a lot of pyrite in it, which is iron sulfide. If a coal is high in pyrite, iron sulfide, when that burns, it puts sulfur dioxide into the atmosphere, then can combine with water and produce acid rain, or weak sulfuric acid, which of course we don't want. But volcanic eruptions can be responsible for putting quite a lot of carbon dioxide into the atmosphere. Running out of space here, so I'll continue here. Certainly animal respiration is a source of carbon. Animal respiration. We breathe. When we breathe out, we're breathing out carbon dioxide. We take in nitrogen, we take in oxygen, but when we breathe out, we're breathing out carbon dioxide, also some water. As we saw in a power plant burning fossil fuels, we see that there's some water some water vapor that goes out that's produced through this combustion, through this oxidation reaction. So animal respiration actually puts a fair amount of carbon into the atmosphere. And it's not only carbon, as in carbon dioxide, but for instance, flatulence in persons or in plants can put out methane into the atmosphere. Now, methane we know is a fossil fuel, but it can also be a greenhouse gas. Also, the belching of bovines, of cows. This has actually been the attention getter for some scientists who are looking at how much cattle belch out methane, which goes into the atmosphere and serves as a greenhouse gas. Methane is a greenhouse gas. So animal respiration is a carbon source as well. The final one that we're going to list here is the weathering of carbonate rocks. There are a lot of carbonate rocks on our planet. And as these things weather, carbon dioxide is released into the atmosphere. There are scientific papers that I've studied with environmental science students that actually note how high the carbon dioxide levels are in mountain streams that are draining mountains that are underlain by carbonate rocks. And so carbonate rocks, as they're weathering, as they're dissolving, actually release a lot of carbon dioxide into the atmosphere. So those are going to be the carbon sources that we mentioned for now. Carbon sinks that we should mention include the formation of carbonate rocks. So as carbonate rocks are forming, a lot of carbon dioxide is being captured and is in that carbon sink, is being held in those rocks. Remember, carbonate rocks are things like limestone. We have a lot of limestone here around Huntsville. And so everywhere we turn, if those rocks were forming now, they'd be taking carbon dioxide out of seawater or out of the atmosphere indirectly. But as they weather, they would be putting carbon dioxide back into the atmosphere. So carbonate rocks can be, if they're forming, they would be a carbon sink or reservoir. If they're weathering, they would be a carbon source. And there are lots of these limestones, lots of carbonate rocks around our planet. The oceans are a significant carbon sink. The oceans and actually lakes also actually take in a huge amount of carbon dioxide from the atmosphere. And specifically in the oceans, it is these tiny little plants known as phytoplankton that are responsible for taking a lot of that carbon dioxide out of the atmosphere. So the oceans are a tremendously significant source. Plants, and I'll say especially rainforests, take an incredible amount of carbon dioxide out of the air. Remember, in the process of photosynthesis, that these plants are taking carbon dioxide out of the atmosphere and are putting out oxygen, which is a great thing for humans because our bodies need oxygen in addition to nitrogen. And so this is a great, huge source or sink for carbon. Takes in a lot of carbon dioxide and, of course, puts out oxygen. But also, in addition to plants, we're going to say animals, because all plants and animals, all life on our planet is carbon-based life. And so anywhere you have living things, you have carbon. And so there's carbon in our bodies. A certain percentage of our bodies is carbon. And the plants and foods that we eat are often carbohydrates. As our bodies process these fuels that we take in, they also put out the same sorts of gases as we've mentioned here as greenhouse gases. And so people and other organisms, for that matter, have carbon in them. So we have plants, especially the rainforest, just because the rainforests are so large and play such an important role in taking carbon dioxide out of the atmosphere. We need to really take good care of the oceans and the phytoplankton that live in the oceans, and also the rainforests, because they take so much carbon dioxide out of the atmosphere for us, just in natural processes. And finally, we're going to mention soils here. And something that we read in class mentioned peatlands, these bogs that we know where peat develops, swampy areas, and permafrost. There are lots of areas closer to the poles that are permanently frozen. And these areas, not only is there's a lot of carbon in those, if permafrost thaws, it releases a lot of carbon dioxide and methane into the atmosphere. And so we really need for the peatlands, these bogs, and the permafrost areas to be healthy and protected, because if they don't do their job, of being a carbon sink, then they become a carbon source. And they're putting carbon into the atmosphere, perhaps at dangerous levels. If we have too much carbon going into the atmosphere, again, that can lead to atmospheric warming. And what we're trying to do is to understand the balance, the fine-tuning that's out there. As we do good science, we can understand the fine-tuning, and then we have the metaphysical decision, as we saw in our study of the ozone layer. We have a metaphysical decision based upon what we learn in science, this fine-tuning. What are we going to do about it? Are we going to try to understand and maintain that fine-tuning? Or are we just it doesn't matter? And so this is critical that we understand not only the greenhouse effect in the atmosphere, its positive aspect of keeping our temperature in a livable range, but the negative aspect that if we put too much carbon dioxide into the atmosphere, perhaps through the burning of fossil fuels, then we lose the fine-tuning. We get things out of balance, and that can lead to atmospheric warming, as we see in the diagram. So the reason that we added the carbon sources and the carbon sinks is we need to realize that it's not a puzzle that has kind of one big piece. It's not just humans burning fossil fuels, but there are a lot of things that are putting carbon into the atmosphere, taking it out of the atmosphere. And so we want to understand that so that we can be doing good science and also understanding the fine-tuning that's out there, but making the decision, the metaphysical decision, to be wise stewards of the environment that we have around us and of which we are a part. Thanks for listening. I hope you find this helpful. Have a great day.